This problem, we're going to take a look at this related rates problem. Kevin stands at a street corner. Brittany stands 240 feet to the east of Kevin when they first see each other. At the same time, Brittany runs west at a constant 8 feet per second, while Kevin walks north at a constant 3 feet per second. The first part of the problem, how fast is the distance between Kevin and Brittany changing when Kevin has walked 60 feet? And be sure to give the units of your answer. All right, for this problem, we're going to kind of go the steps through how to solve a related rates problem. The first step for solving a related rates problem is to draw a diagram just to indicate what's going on. All right, so I'm going to do this in two steps. So over here to the right, let me draw this related rates problem. So here we have our axes. Okay, and so the initial starting values, Brittany is here in orange, and Kevin is here in green. And then Brittany starts running this way at 8 feet per second, while Kevin starts walking this way at 3 feet per second. And then at some future point, Kevin is maybe here, and Brittany is maybe here. And the question is, how fast is the distance between them changing at this moment? Okay, and we're also given that this moment occurs when Kevin has walked 60 feet away from the corner. Okay, now that's with the numbers. So let me redraw the picture here without the starting and ending values. So we have Kevin is here in green, and Kevin is some distance away from the origin. Brittany is over here on the axis down here, and Brittany is some distance away from the street corner also. Brittany is coming in this way at negative 8 feet per second, while Kevin is moving upward north at 3 feet per second. And the question is, how fast is the distance between them changing? All right, so let's figure out, so that's the picture. The next thing that we should do is to write down the given values of any variables and any rates of change that we know. All right, so we're given that dk dt is equal to 3 feet per second when Kevin has walked 60 feet. Okay, now that's all well and good, but I'd like to know how much time has elapsed. Now, how much time has elapsed when Kevin's walked 60 feet? Well, he's gone 60 feet. He's walking at 3 feet per second. So the amount of time that's elapsed is going to be 60 divided by 3, or 20 seconds. So we're given that the Kevin's distance from the street corner is increasing at 3 feet per second after 20 seconds. We're also given that dB dt, that's going to be a constant negative 8 feet per second. And it's negative because Brittany is getting closer and closer to the corner. And that occurs at the same moment when t is equal to 20 seconds. Okay, so that's what's we're trying to find, or that's what's given. And what we're trying to find is ds dt, where s is the distance between Kevin and Brittany. All right, is there a relationship between s, k, and b? And clearly, we can use the Pythagorean theorem. So s squared is equal to k squared plus b squared. And I could differentiate this directly, but instead I'll solve for s. S is equal to the square root of k squared plus b squared. All right. So the next step is we differentiate with respect to time. And so ds dt is equal to derivative of square root. That's going to be 1/2 of the thing inside the square root to the minus 1/2 times the derivative of the inside. The derivative of k squared with respect to t is going to be 2k times dk dt And the derivative of b squared with respect to b is going to be 2b times db dt. Okay, and now we can almost plug in at this point. So we know dk dt, that's given here in green. We know k, that's given in green. We know db dt, that's given in orange. What we don't have yet is what the value of b is. Okay, so that, however, we can figure out. So when t is equal to 20 seconds. So how far does Brittany run in 20 seconds? Brittany travels 20 times 8, which is 160 feet. And so B is equal to, okay, now back to the original problem. Brittany was originally 240 feet away from the corner. She runs 160 feet toward the corner. And so that means B is 240 minus 160, which is equal to 80 feet. Okay, and so with this information, we can now plug in. So we have that dsdt is equal to, we're coming back to the bottom of the page. I think everything I need is on screen. We have 1/2 times k squared, 60 squared, plus b squared is 80 squared, whole thing to the negative 1/2, times dk 2k, so 2 times 60, times dk dt, which is 3, plus 2 times b, which is 80, times db dt, which is negative 8. And so now it's just a matter of plugging into a calculator and seeing what we get. And if I did the arithmetic right, that is 4.6 feet per second. Okay, so that is the solution for the first part of the problem. So that's uh, one way of going about this. So this is option one. So alternate solution. Alternate solution would be to start with s squared is equal to k squared plus b squared. And then let's just go ahead and take the derivative. The derivative is going to be 2s times ds dt is equal to 2k times dk dt plus 2b times db dt. All right, and so 2 times k, it's 2 times 60 times 3, then 2 times 80 times negative 8. That equals 2 ds dt, 2 times, okay, now notice that if I tried this alternate approach, I have to figure out the value of s, which I did not have to explicitly figure out before. So with the method in black that I did here, I didn't have to solve for the value of s. With this method in red, I do have to solve for the value of s. That's not too bad. The value of s at this point is 60/80 by the Pythagorean theorem. That's equal to 100. And so I would get this 2 times 100 times ds dt is equal to 2 times 60 times 3 plus 2 times 80 times negative 8. That should look an awful lot like what I had on this line in black. And so if I just do the algebra, ds dt is equal to negative 4.6. And this is a rate again, so I need distance over time as my units, feet per second. And that is going to be the rate at which the distance is changing. So it is decreasing at 4.6 feet per second. Okay, so that's the first part of the problem. Second part of the problem. Let theta be the angle at which the so let me redraw the picture on this fresh sheet of paper so I still have it. So here's B, here's K, and theta is the angle between Brittany and the corner and Brittany and Kevin. So there's my angle theta. How fast is theta changing when Kevin has walked 60 feet? Okay, and so is there a relationship between theta, K, and B? Yeah, so we can show that tangent of theta is equal to K over B. Now K and B are both changing. So neither one of these is a constant. So if I now take the derivative with respect to time, secant squared theta times d theta dt is equal to the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Okay, so once again, we have almost everything we need, and here's the picture that I had before. So here's my 60, 80, 100. So I've got almost everything I need. What I don't have yet is the secant of that angle. So this part over here to the right is the one thing that I'm missing. All right, now what's the secant of this angle? Well, the cosine of theta is going to be equal to adjacent over hypotenuse, so 80 over 100, or 4/5, and therefore secant of theta is 5/4. And so with that, I now have all the information I need to be able to solve the problem. Secant of theta, that's 5/4 quantity squared times d theta dt. On the left-hand side, I now plug in the information that I had before, which I'll try to get on screen here. If I fold this over. So dk dt was given to be 3 feet per second. B we figured out to be 80 minus K is 60. dB dt is -8 all over B squared, which B was again 80. And so now it's just a matter of solving for d theta dt. And if just plug into a calculator to do the arithmetic, this works out to be 0.072. Now, again, I can't just write that as my answer. This is a rate. And so this is the rate at which an angle is changing. My units are going to be radians per second. And so that is the rate at which theta is changing at that moment.